All right, today we're going to take a journey to the very edge of space, time, and honestly, our own understanding. We're going to be talking about one of the most powerful and mysterious objects in the entire cosmos, the black hole. This whole thing kicks off with a really simple but totally mind-bending question. It was first asked way back in the 18th century, and it set us on a path to completely rethink the fabric of the universe. So, what if an object's gravity got so powerful that not even light, the fastest thing in the universe, could get away? Okay, so let's dig in. Where do we even begin? Well, the idea of a black hole didn't just pop into existence. It actually evolved from an older, kind of stranger concept. Now, this is where it gets really interesting. The original idea, this dark star, was pretty straightforward. Just imagine a star that's so big and heavy that its escape velocity is faster than the speed of light. Makes sense, right? But then Einstein's general relativity came along and completely changed the game. Suddenly, it wasn't about the object itself anymore, it was about the space around the object. The modern idea is that a black hole is a chunk of space-time that's been warped so badly, it's basically folded in on itself. And that lands us on our modern definition. Put simply, a black hole is a place where gravity is so strong that nothing, and I mean nothing, no particles, no energy, not even light, can escape. It's all defined by this boundary, this true point of no return, which we're about to get into. So let's talk about that boundary. It's called the event horizon, and honestly, it's the feature that makes a black hole one of the weirdest things in the entire universe. I want you to imagine you're a little particle, just floating through space. Way out, far from a black hole, everything's normal. You can go left, right, up, down, anywhere you want. But as you drift closer, space-time itself starts to flow, getting pulled toward the black hole. Think of it like a river that's picking up speed as it gets closer to a giant waterfall. The nearer you get, the stronger that current is, and fewer paths lead away from the edge. And once you cross that event horizon, well, that's like going over the waterfall. Every single possible direction you can move now points in only one direction, inward. There's no turning back. And the crucial thing to get here is that the event horizon isn't some physical wall you'd smack into. It's not a surface. As it was first described back in 1958, it's a perfect unidirectional membrane in spacetime. It's a location, a point of no return. Once you're past it, you literally cannot go back. So where are all those one-way paths headed? They all lead to this singularity. This is the theoretical heart of a black hole. A place where all of its immense mass is crushed down into an infinitely small point, a point with zero volume. It's here that our entire rulebook for physics, for space, for time, it all just completely breaks down. Okay, I know what you're probably thinking. This all sounds like something straight out of science fiction. If black holes are invisible because they trap light, how in the world do we know they actually exist? Well, the search for them has been this incredible piece of cosmic detective work. We can't see them directly, so we look for the chaos they cause. We see stars orbiting while seemingly nothing at incredible speeds. We can detect these super bright X-rays from gas that gets heated to millions of degrees as it spirals in. We can even hear the universe shake, these ripples in space-time called gravitational waves when two black holes crash into each other. And most amazing of all, we can now take a picture of the shadow a black hole casts on the glowing gas behind it. And you can really see the progress here. It's incredible. We went from our first strong hunch, Cygnus X1, back in the 70s, to literally hearing two black holes merge in 2015. And then the big one, the stunning first ever direct image of a black hole's shadow in 2019. We've gone from thinking they exist to actually seeing their silhouette. Speaking of seeing them, check out this number, 4.3 million. What could that possibly be? Well, that's not a distance. That is the mass in suns of the supermassive black hole that's sitting right in the middle of our own galaxy. That's right. The Milky Way has its own giant, Sagittarius A star. And in 2022, we got our own family portrait, confirming without a shadow of a doubt that we've got one of these cosmic monsters right here in our own galactic backyard. But here's the thing. Even after finding them, even after taking their picture, this story is far from over. In fact, these incredible discoveries have only opened up deeper, stranger mysteries, pushing us to the absolute edge of physics. Just when we thought we had these things figured out as one-way doors, Stephen Hawking came along and just flipped the script. He realized that when you mix in quantum mechanics
Black holes aren't perfectly black. They should leak a tiny, tiny bit of energy, what we now call Hawking radiation. And over unimaginable amounts of time, they can actually shrink and completely evaporate.
And that idea, it leads to one of the biggest paradoxes in all of physics. Think about it. If you throw a book into a black hole, all the information that made it a book, the story, the words, the ink, it seems like it's gone forever. But if the black hole eventually disappears, where does all that information go? Does it just get deleted from the universe?
And this is the heart of the problem, the information loss paradox. It's a clash of the titans. On one side, you have general relativity, which says, yep, that info is gone forever. But on the other side, you have quantum mechanics, and one of its fundamental rules is that information can never, ever be destroyed. It can be scrambled, but not erased. So who's right? Is one theory wrong, or are they both just part of a bigger picture we can't see yet? And that's pretty much where we are right now. Black holes have transformed from being just a weird theoretical idea into a real cosmic laboratory. They're forcing us to ask the biggest questions imaginable about space, time, and reality itself. And as we keep trying to peer into their shadows, you just have to wonder, what other secrets are they waiting to tell us?